In example 5, our goal is to determine the intervals over which this function is concave up or concave down, so we're going to use the concavity test. First thing we need to do is find the domain. There's parts of this function that are polynomial, the x squared portions, but there's also a natural log. So the natural log has a restricted domain of positives only. So the domain is going to be just from 0 to infinity, and that's because of the natural log. That's the domain of natural log. So I use the restricted domain of that restricted function there. Alright, so after I have the domain, I want to find the first and second derivatives. Okay, so first of all, f prime of x is going to use the product rule, so we're going to have 4x times natural log of x plus 2x squared times 1 over x, that's the derivative of natural log, minus 10x. Let's get that simplified before we find the second derivative. That's 4x natural log of x plus, that would be 2x minus 10x, so I can simplify one more time. 4x natural log of x minus 8x. Okay, so I've got my first derivative simplified. Let's find the second derivative. Okay, for space, since we're at the bottom of a page right here, I'm going to do the second derivative over here. So the second derivative will be, okay, so 4x, that's 4 natural log of x plus 4x times 1 over x minus 8. So 4 natural log of x plus 4 minus 8, or 4 natural log of x minus 4. So we have our second derivative. Step 3, we're going to take the second derivative. We're not going to use the first derivative for anything except finding the second derivative here. So we're going to use the second derivative and both set it equal to 0 and find out where it fails to exist. So, the second derivative fails to exist. There are no denominators to worry about here, so it's going to fail to exist only where it's not in its domain. So it fails to exist for x less than or equal to 0. Those are already not in the domain. And that's just because you can't plug those values into natural log, but you had a natural log originally. Okay, so there are a few places where the second derivative fails to exist. They just are not new values. They were already excluded. So if I have negative values or 0, they're not going to work. All right. Next, let's look at where the derivative is equal to 0, second derivative. So we have our 4 natural log of x minus 4 equals 0. So that would be 4 natural log of x equals 4. Natural log of x equals 1, which gives me e as the inverse function. Since the base is e, if you have e, natural log of e, you get 1, so x is e. So I have one critical value. This is a second order critical value. Alright, now that I have my second order critical value, we're ready to go into step 4, constructing our table. So I need test intervals, test values, sign of the second derivative. I'm going to emphasize that by putting f double prime there, second derivative sign, and then I'm not saying increasing or decreasing as my conclusions, we're saying concave up / down. Alright, so just the C to abbreviate concave. So test intervals, we were originally going from 0, that's my domain, was originally, remember, just 0 to infinity, so we're not looking at negative infinity. So we're going to go from 0 to e, and then we're going to go from e to infinity. So there's one critical point, one partition, so 2 intervals. So I need something between 0 and e, so I could choose 1, and something between e and infinity. To make it easy to plug into the second derivative, I'm going to choose e squared, because I can plug that in easy. Or you could choose 5, for example, if you didn't want to do it in your head. Okay, so I'm going to plug these into the second derivative over here. Alright, so I know that the natural log of 1 is 0, so that's 4 times 0 minus 4, that's going to be negative. If I plug in e squared, the natural log of e squared is 2, 4 times 2 is 8 minus 4 is 4, positive. Okay, so again, any value that you can plug into the interval is going to be fine. What you care about is if it's positive or negative to get your conclusions. So this one's going to be concave down, and this one's going to be concave up. So my conclusions are that we are concave up on e to infinity, and we are concave down between 0 and e. Okay, so those conclusions come from the test for concavity in that fourth step. The fifth step is just classifying my second order critical value as an inflection point. So if I change, there's not two types. There's two types of extrema, max and min. There's only one type of inflection point. It's just whether or not I change. So I did change. I went from positive to negative. That changed. So that does mean that there is an inflection point at x equals e. That is the x value where there was a change in concavity. So there is a change there. So that means I do have an inflection point. Okay. Now let's look at our graph. So I know E is about 2.7, so it's somewhere here-ish would be where E would be on this graph. And I should be able to see that the concavity, this is cupped downwards up until that point. And then after that point is where it is cupped upwards. So the rest of this function from e to infinity has that upward cupping. So we're not talking about where it's increasing and decreasing, we're talking about where the shape of the graph curls from a downward curl to an upward curl.